Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so let's get this going today. We're very delighted to have Avi Vigdisson here. I suspect we don't do long introductions here. So he's a well-known geometer who will tell us a little bit about theoretical computer science today.
I don't need this, right?
You don't need this. You're already set. Did you turn it on?
I don't know. Do you think I need it?
Yeah.
Okay, is this?
Huh?
No, the other way around.
Yep.
I flip, you flop. Hello. It's too loud, no? It's.
It'll get adjusted.
Yeah, it'll. Okay. So from a geometer like Madhu, it's an honor to be introduced as a geometer. So this is a sort of experiment. You are the guinea pigs. I decided to give you 3 talks. So these are 3 talks. So maybe what it will mean is that you will not understand anything. Maybe actually, what my hope is that each one of these topics will give you a taste for finding out more about each of these things. It's a talk I gave just once in a math department, and I wanted to just impress mathematicians on the connections that classical math, has with theoretical computer science. And the most classical math you can get is if you go back to the Greeks and talk about Euclidean geometry. So the 3 topics I'll talk about, I mean, they're all big, and I had a little thing to do with each of them that I'll tell you about. And one of them is about the connection between, so in each of them there's a connection between some problem of theoretical computer science, or what the kind of discrete stuff we do with Euclidean geometry. So here's the connection of parallel repetition of games and periodic forms. I'll at least explain what the notions are. The second connection between belief propagation, compressed sensing, given expander graphs, and this problem of L2 sections of L1, which I'll explain. And the third thing is a connection between problems of matrix rigidity and locally correctable codes with the most basic problems of geometry, which is incidences between points and lines. I think that Microsoft really believes in these flat rooms where the people in the back have no chance of seeing anything. It seems they imported this technology all the way from Redmond to. Yeah, in fact, yeah, that's right. So focus on the red stuff. It's. Okay, so I know that Madhu told me that I have 2 hours, so feel free to. So really ask questions and Okay, so there's some slides. No, you don't get to ask. Okay.
When you say geometry,
yeah.
What do you informally mean?
Yeah, so of course, yeah, that's a really good question, and there are tons of connections between theoretical computer science and geometry. So here I just want to talk about problems of Euclidean geometry. Still, there are lots of things that I just want to talk about few things I know about. Okay, so that's, but you'll see the kind of.
So like spaces, lines. And
yeah, spaces, lines. Yeah. Just, well, you'll see the problems. The problems are just well defined, and they are geometric problems. Okay, so some slides I stole from Guy, obviously a connoisseur. So maybe that's for Manup. Yeah, I like to steal slides. So what do you see here? You have to look at it to stare at it, and you see that this is an algorithm, right? And this algorithm is trying to solve an optimization problem. And the optimization problem that it's trying to solve is the isoperimetric problem, right? What's the minimum surface area that it can have, this bubble, given its volume. And we know the answer. I mean, you see the answer. It's, the minimum area is just when it's a sphere. So that's a simple problem. By the way, you should all verify that you can prove that this is true, that this is the minimum surface area. But here's the harder problem, is when you have lots of bubbles. When you have lots of bubbles, this optimization problem is really much more complicated. Right? You still have these bubbles, they each have its own volume, and they want to reorganize themselves in such a way, that's what physics tells us, they want to reorganize themselves so that they have least surface area. And there are lots of constraints there, it's really complicated. So what arrangement of bubbles give you the least surface area? So that's a complicated problem. And the first thing you should ask, who cares? And actually, because of 2 centuries or so of work, you realize that lots of people care. So it's, this problem and related problems come up in lots of important areas. I'm not going to go into there, but it's a fascinating history. And Lord Kelvin, even if we restrict ourselves to 3 dimensions, found the optimal structure. And 100 years later, even more optimal. So you can see it's really complicated. By the way, this design of Weary and Phelan, with the intuition from geometry, from chemistry, sorry, is what you see if you look at the China Olympic swimming pool thing. That's where the origin of the design came from their solution of this bubble problem. Now, all these solutions, Kelvin and Weary-Phelan and many others, are not just minimum surface area or trying to achieve minimum surface area, but they are also periodic in the sense that you shift the solution in space and then you can shift it again as many number of times you want in several directions. So we are going to be interested in periodic solution to this minimum surface area. And now with periodic solutions, well, you can have many types of periods, any lattice you pick in space.
So at this moment, we are considering all bubbles at the same volume?
Yeah, so I'll define it, but yes, yeah. And we are going to consider the simplest lattice, just the integer grid. Okay, so this is our problem. You want a minimum surface area of a body with unit volume, just volume 1, that's periodic according to the integer lattice. Okay, so the simplest example I can give you is in 2 dimensions, because 1 is boring. So 2 dimensions, and we are, what kind of structures can you have of full unit volume here? So squares are the most obvious ones, right, that are periodic. I hope everything is clear to everybody, so ask me if not. So in 2 dimensions, square is definitely a periodic solution, the most obvious periodic solution. What's the surface area here? It's 4, right? 1. Okay. Anybody has an idea of another solution?
The surface area here is really just a perimeter.
Perimeter, yeah, that's a very good comment. So area in 2 dimensions is just, yeah. Here the volume is area and the area is perimeter. Yes, thanks. Any other shape that's periodic?
Hexagons.
Hexagons is good. But just before hexagons, I want to tell you that there are lots, infinitely many shapes that are periodic. So, if you are looking for the best one, it's not so obvious how to get one. So there are any number of these. In this case, this is a little bigger than 4. But as suggested, hexagons are good, particular hexagons. There are several. And Cho showed that if you take these hexagons, you get surface area, in this case perimeter, which is actually smaller than 4. And moreover, so it's just a few % better, moreover, it's optimal. So we know this is the best solution for 2 dimensions. What about 3 dimensions? Now, 3 dimensions is really interesting because if you are a packaging company, I know I'm in a big corporation here and they care about expenses. So if you are in in a packaging company and you manufacture things that should, pack like stack in trucks and boats and ships and so on, then You know, we know they manufacture them in rectangular shape, but are they doing the best they can? Maybe they can, you know. Suddenly, if they have this base, they'll save money, a few percent. So maybe we could do even better. So let's look at this problem. So in D dimensions, there are two obvious bounds, right? I mean, suddenly we know we can do boxes, in which case the surface area is just, right? It's unit volume. So we have 2D unit area surfaces. That's the obvious upper bound, linear in D dimensions. What's the lower bound? Well, suddenly if you have a unit ball, I mean a unit volume, the least surface area will be a sphere. It doesn't pack, but that's a lower bound for any solution, periodic or aperiodic. There's a big gap between the two. It's a square root D. The dimension goes, it's a big gap. So where is the optimum? Who votes for linear? So I'll give you three options: linear, square root, and something in the middle. Who votes for linear? Who knows the answer? Anybody has an opinion, doesn't matter. Yeah, people are cautious here.
The answer I thought was 2D.
Yeah, no, I think it's certainly far from obvious. But anyway, what the first paper I want to tell you about, the result with Kindler, O'Donnell, and Rao, is that actually the lower bound is tight. So here, let me interpret it for you. They are spherical cubes. They are physical objects that have the surface area very close to that of a sphere, and they pack perfectly like a cube does. So that's what the packaging company should use if they were actually doing boxes in dimension 2000. And I will not tell you about the construction. It's a probabilistic construction, and it's a great open problem, I think, to know what it looks like. It's a probabilistic construction. It generates really weird things. But anyway, they exist. And I want to tell you about the connection to TCS, not about the construction, but you can ask me later. That's the open question I want to popularize here. But let me just give another interpretation of this result with sort of application to a problem called rounding. So the result is clear, what, you know, this magic that happens here. Excuse me?
Do you know it for 3 dimensions on the side?
No, we don't know this, but for 3, of course, you know, they are all constants, and we have a construction, an ad hoc construction for 3 dimensions, explicit one, which beat, you know, whatever was well known before, yes. But we don't know if it's optimal. Yeah, we do. So in the paper, we have separately a one for 3 dimensions. Yeah. Here's another problem, which comes up a lot, in fact. Basically, what you want to do is you have real vectors, and you want to make from them integer vectors. So in 1 dimension, we are used to it. So you want to round a number. And you round it to the closest integer. So here we want to round a vector, you know, so that every coordinate is rounded up or down. But we want to do it in such a way that when we round 2 guys, you want a coordinated thing. That if 2 guys, you know, say, let's meet in the corner of this and that, that avenue and that street, they'll meet in the same place. At least if they are close, right? So that's the problem. So we want that for every 2 points, the probability, so it will be a randomized strategy, a randomized rounding. We want the probability that they will not meet to be related to their distance. And what happens from you get directly from the previous result that if you round 2 things, if they are, you know, in the same structure, the periodic structure, then the probability that they'll be different is just a constant factor of their Euclidean distance. It's very different than what you would obviously get if you use cubes or something. This result will depend on the dimension. There'll be square root D here. So you don't need it. That's dimension independent, this round. OK, so where is it coming from? I'm not going to show you the construction. I want to show you where it's coming from, which I find very bizarre. But how you know, some TCS result inspired this kind of geometric construction. So I'm going to tell you about linear equations. OK, so everybody knows what linear equations are. We have some linear system, M linear equations in variables Z, let's say, so n variables. And actually, the first thing I want to tell you is for those who are maybe from somewhat, related areas to complexity theory, it's sort of an excuse why we still don't solve our big problems of the field. Why is it hard to tell if a problem is hard? So here's the problem you met many times since high school. You have a system. I give you a linear system, and I can ask you several questions about it. And these questions look roughly the same, and nevertheless, to answer them looks very different. So if I ask you to solve it, is there a Z, a solution to these linear equations? That's an easy problem. At least we learn how to solve linear systems, Gaussian elimination, and so on. That's an easy problem. OK, but suppose I ask you, is there a Z, is there a solution that satisfies 90% of the equations? That's a much harder problem. That's an NP-hard problem. That follows from the PCP theorem. Now I can ask you, is there a solution that satisfies half the equations? These are over GF2, right? Is it hard or easy? Is it hard to tell whether there is a solution satisfying GF2?
GF2.
Well, who votes that it's an easy problem? OK, so you know that. Why are you so silent? Yeah, it's better than it. It's a trivial problem because you don't have to look at the input. It's always true, right? So it's always so that's peculiar. But actually, what we know is much more than that. So we have the Hardness theorem, which says that actually everything is hard between here and here. So stating it as the following, if I give you a linear system, it's NP hard to tell whether you are close to this, whether the half plus epsilon satisfying solution, or whether there is no 1 minus epsilon satisfying solution. So just distinguishing the extremes is NP hard. And this 1 minus epsilon sort of hardness, this gap, it's very useful, but sometimes it's not useful enough. So sometimes when we have a hardness result and it's not enough, we want to create an even harder problem. So that's a problem of hardness amplification. And it has many variants, and I'll tell you about one of them. And that's the variant with linear equations. And we look at a particular, so this is a frog or a cow? Yeah, I understand, but that was obvious. I just didn't recognize the animal. Say hi. OK, so we are in the situation of very specific linear systems. There are linear systems with two n variables, the x variables and the y variables. And every equation has just two variables in it, one x and one y. OK, that's how it looks like. So we have m linear equations in these variables. And suppose I promise you that this is a sort of a hard case. This is a situation where no solution satisfies more than 1 minus epsilon of the equation. OK? Suppose we know that. I want to interpret this as a game where it's hard for somebody to do something. And this somebody is actually Alice and Bob. OK, so here's Alice and Bob, and here's the game. What I, the referee, do is I pick a random equation from this system. OK, let's say the ith one, the jth one. I pick the random equation, and I give the x variable to Alice and the name of it, and the y variable to Bob, and I ask them, what value will satisfy this equation? OK, now you see this wall. They can't talk to each other, so they don't really know which row I picked. They just know the name of the variable. Maybe it appears 20 times, so they don't know which one. So they can coordinate a strategy ahead of time, but after that, they cannot talk to each other. What's the probability that they'll succeed? Namely, that this will satisfy the equation. What's the best probability that, for the best strategy they have? What's the probability that they'll succeed? If no solution satisfies more than 1 minus epsilon of the equation.
1 minus epsilon?
Yeah, 1 minus epsilon. it's actually very easy to see that there is no way that, I mean, it's really easy to see that whatever strategy they have actually corresponds to an assignment to the variables. The best they can do because they cannot talk to each other. So the probability that I'll accept or that there'll be, that this equation will be satisfied for the best strategy is 1 minus epsilon. And this is the kind of thing we want to improve. 1 minus epsilon versus 1 is not a big gap. So what we would like is a big gap from 1 to maybe epsilon, from 1 to a very small number. How can we do it? So what's the standard way of making things harder? You just repeat. If something is hard, for somebody, you let them do it 10 times, and it's harder. That's exactly what. So let's do it. So here's the repetition of the game. So here we have the same system, exactly the same system of equations here, which has no very good satisfying assignment. And now the game repeated d times in parallel, that's very important, in parallel, is where I pick at random, not one equation, but d equations at random. And I give Alice the dx variables, and I give Bob the dy variables. And I ask them to provide me with values so that all of these equations will be satisfied. Right? The obvious thing. Yes?
K the same as D?
No. Where's K?
Yeah, it should have been.
Oh,
first
this.
line.
Yeah, sorry. This is D, of course. So, yeah, very good. So that's D. Thank you. I picked D equations. So what now is the probability that they get the answer right? If for the one-shot game, it's 1 minus epsilon. Well, I'll pay you later. Actually, there's no time to really impress on you how subtle this question is. It's extremely subtle, and for a long, long, long time, it was not even clear that this decays with D. It was an open problem for a long time whether this goes down to 0 with D. And the breakthrough came when Raz proved this very famous parallel repetition theorem, showing that it doesn't only decay in D, but decays exponentially in D. But the way it decayed with Ran's result was something like 1 minus epsilon to the 30. So that it's not 1 minus epsilon to the D, as Eli, who is maybe he takes after his PhD advisor, is very optimistic. It decays exponentially, but not in 1 minus epsilon. And then there were some improvements, and the best improvement due to Rao, Holenstein and Rao, is that this 1 minus epsilon squared here. Now, what Eli said is what we'd like to see. We want to see 1 minus epsilon to the D. It seems like it's not a big difference, but it's a real big difference. If you know the connections, which I won't tell you about, there is a big question. Many people tried for a long time to shave these two out of the, or prove that nothing better is possible. And the next development in this really phenomenal sequence was a paper of Feige, Kindler, and O'Donnell, who said that actually, under some condition, we can prove that this is tight, cannot be beaten. And this condition is that spherical cubes exist. So they made the connection to geometry. They showed if these weird objects exist, then we can prove the lower bound. This is actually tight. So this stood for a while. So nobody knew if spherical cubes exist. Okay, and then as usual, Raz came to our help and said, well, forget spherical cubes. I can prove that this is a lower bound. So he proved that this is tight. So he matched his own result. So that you cannot beat this. It's very, anyway, I won't go into the reasons for this, but he resolved the problem. And then what we did is realize that, you can look at Ran's proof and sort of reverse the arrow here. And from the method of proof actually construct the spherical cubes. What we did is, in some sense, a continuous analog of his discrete result. So that's how, these weird objects came into existence. And that's a connection.
Is there even now the simple proof
simple construction?
In some sense, yes. It's the same inspiration. I mean, the analysis is simpler. The construction is exactly the same, and the analysis is simpler. Absolutely, yeah. Yes. Yeah, even our solution is different. It runs sort of distribution is not optimal. So, yeah, the new two solutions to spherical cubes are the same, and the analysis in a long Clartag is somewhat simpler. Yeah. Okay, that's the end of this story. So, if you have questions about it, yes. Excuse me. If you, in some sense, there are some pictures in the paper. They are extremely bizarre objects. Extremely bizarre. So.
And are these convex?
I'm not sure if they are convex.
What?
What? No, what we have are not convex, but it's not clear that you cannot convexify them. That's what I mean, yeah. Okay. They are not convex as they are, yeah.
Why is that so funny?
Well, you'd expect. I don't know.
You're trying to minimize surface area, so you think that you make it right. You think that you'd like to do something like that, and the surface area will.
Looks very reasonable. That it should be convex, but we don't know. Yeah, sorry.
So, are there little wiggle constants in those inequalities on the lower right, or do you mean?
Yeah. There are some constants, but.
There are constants in the exponent.
Yeah, there are constants even in the exponent. Yeah, but it's that's the right option. Yeah, but you should think. Yeah, there are constants in the. The way you should think about is the question is when will this probability be a constant? What is the right relationship between epsilon and d? And it turns out that epsilon should be 1 over square root of d for this to become a constant. Okay, that's what it really means. Also, it's not. I oversimplified. That's the advantage of PowerPoint. I think. I really think is that it forces you to simplify your formula.
So can the cube be like a polynomial number of faces, or actually with respect to the dimension?
Ours is exponential, but
also like if the problem requires that it is a polynomial number of faces, maybe there's another lower bound of interest.
Maybe, but it's an interesting question which I didn't think about. But in our case, there are exponential number of faces.
I mean, we don't know if it's got. I don't know if it's not.
Well, it's really a surface, but you can make it. You can sort of straighten some faces. In fact, you're right that it's not a polytope what we generate, but it could be made a polytope.
So in 2 dimensions, you can approach the improved solution hexagonal by sort of starting with a frame.
That's
and,
right.
Letting them
relax according to the
I mean, is it hopeless to try and?
Even in 3 dimensions, you should see what these people are doing. I mean, even our 3-dimensional solution, which does start from some, some idea and then relax. Even this is quite complicated. So I cannot imagine what happens in higher dimensions. So I don't know. And the pictures in the paper are from, where you run some software. I mean, Ryan O'Donnell decided he's going. Yeah, so I don't know. Okay, good. So this, clearly we have only 2 more topics. So, but actually I planned it sort of. Anyway, we'll do what we do. You tell me when to stop. It's okay. Okay, so I want to talk about something completely different, and this is the Euclidean sections. So you should see this is the L1 ball, and it's being cut by a hyperplane, by the subspace. And when you cut it by the subspace and you look at what you find there, you see a ball. So somehow, despite the fact that this L1, when you look at the subspace, it looks like a ball. So I'll explain it more formally. There's no body, right? Okay, so can I write on this?
There's one right behind the screen.
That's okay. No, so you all remember the Cauchy-Schwarz inequality, right? Okay, so that's all you need to remember. So the question is, how tight is the Cauchy-Schwarz inequality? It tells you that L1 norm is at most, in n dimensions, is at most square root n times the L2 norm, right? How tight is this? Is this a tight inequality? Yeah, there are examples where it's tight. But there are examples where it's really far from being tight, right? If you had a unit vector, one with lots of zeros, and it's really far away, so like square root n far away from. So can it be tight on a subspace? That's the question here. And it turns out that this is a classical result, that if you take a random subspace of Rn of dimension n over 2, then L1 and L2 will be the same. So the Cauchy-Schwarz inequality will be tight with the square root n factor. So that's what it says here. For every vector in this subspace, L1 and L2 will be exactly within square root n of each other, like Cauchy-Schwarz tells you, up to maybe a factor of 2 or something. So that's it's not so easy to prove. Just one interpretation which will be useful for us later, what it means about the vector. So it's not a unit vector. It will be really a vector where the mass, the L2 mass, is sort of spread around. So lots of coordinates have roughly, are roughly the size 1 over root n in magnitude. They are a linear number like that. So that's what this, all elements in the subspace look like, all of them. Okay, so they exist, these things. And that's a result in geometry. And what we would like, so it's a random, so let me just say, it's a random, it's a statement about a random subspace. You may wonder how to represent a random subspace. So you can represent it as a kernel of a matrix, n over 2 by n matrix. And it turns out that this result applies even if the numbers in this matrix are just plus minus 1. So you can really concisely describe such a subspace. A random plus minus matrix, look at the kernel, it has this property. So it turns out you can describe them, and that works for most random sign matrices. And the big open problem here, so you should work on the open problems at the end, right? I mean, find explicit spherical cubes, find explicit, matrices of this type. So that's what we are after. I'll tell you some things about it, but I'll also motivate it. So that's what we want to. So here it's again. And I want to, there will be 3 issues here that come up, this distortion, dimension, and randomness. So let me tell you about all 3. We are looking at subspaces of Rn. We have this parameter, which is the distortion. So the distortion is just how far are you from being tight according to the Cauchy-Schwarz inequality. So if this is a constant, if this thing is a constant, this distortion, then you are really tight. All vectors are within square root of n of the square root of n in L1 and L2, between the L1 and L2 norms. So that's a distortion of a subspace. The dimension is obvious what it is. So let's look at the results I just mentioned before. If we pick a random subspace, let's say the kernel of a random sign matrix, then the dimension will be n over 2. The distortion will be a constant, namely it will be tight. The Cauchy-Schwarz inequality will be tight on the subspace. And it's a random, it's a random structure. So let's count the investment in terms of random bits there. This is a n squared, roughly n squared bits. And actually, it was very nice for me that 2, geometers, Austin and Millman, started, because they couldn't generate these things explicitly, said, well, let's try to reduce the randomness. And when this happens, when mathematicians are asking this question, somehow we penetrated some something. And they did some work. But let me tell you about, we cannot, achieve optimal in all 3 cases. What we want, really, we wanted deterministic solutions. This should be 0. And the other 2 should remain the same. And the best in all fronts, I'll tell you the state of the art, is if you want a deterministic solution with constant distortion, so you're tight, the Cauchy-Schwarz inequality is tight, the best we know explicitly is to get something of sublinear dimension. That's a result of indic. If you want deterministic solution that achieves linear dimension, then you have to pay in the distortion some polylog. And if you want the best of these, then the best we can do, and I'll tell you a little bit about it later, then you can reduce the randomness from n squared to any power of n, but still a constant power of n. And what's interesting, what?
Is n over 2 something special?
No, it's not.
So epsilon n would work?
Epsilon n would be interesting. We don't know even how to get epsilon n. We see that this is not achieving
Right,
epsilon.
but what about the other constructions? The
You want high dimension, so you want 1 minus epsilon n?
So 1 minus epsilon works?
Yeah, 1 minus, well, yeah. If you start, there is a trade-off here, yeah.
And it's interesting to minimize this epsilon, or no?
Anything, in some sense, we are lacking techniques, right? So it's, we don't know how to do deterministic constructions that come close to
No, I mean
this.
the randomized construction, how small is epsilon?
Yeah, if the random, you can have a trade-off here. You can get 1 minus epsilon n space, dimension, and this will increase. Yeah, and the trade-off is known and it's optimal in the randomized construction. It's just tight.
Is it one of those things where it's obvious that the randomized is best? Or
No, it's not obvious. Not
so
obvious.
When you say optimal,
But
what do you mean?
that you can prove the other direction. Yeah.
Not that
the
you're
randomized will not.
measuring.
You can
things
prove that
from-
that the randomized construction gives you within a constant the best you would get in any construction.
I see.
Yeah.
So you have
The trade-off is known. The trade-off is known and is achieved by the randomized construction. Yeah. And what's interesting in the connection to us, I mean, there are several connections I'll show you, but one connection that's very important is that in all these results, these 3 results, expanders play, crucial role. Yeah.
Isn't the n, maybe I missed the n squared is the plus minus?
Yeah, random plus minus. So that's the thing I told you before, and these are the improvements of different parameters. Yeah. So expanders play, and I'll show you in what way they come in. But before, and I want to talk about, why look at this problem of Euclidean section? Again, who cares? And in this case, we care. So I want to show you some applications, and then we'll talk a little bit about the solution. So it turns out to be really useful to have such subspaces that have large dimension and small distortion over the real subspaces. So I'll show you applications. So it has to do with the embeddings, which lead to efficient geometric algorithms, and it has to do with the very important buzzwords in the last few years of compressed sensing and with error correcting codes over the reals. So I want to explain these. So let's talk about this low distortion embedding. If you have a subspace, then it naturally induces a mapping from the subspace to the natural embedding of the subspace in the big space. So let's call this mapping G. So it's really, let's think about it as a mapping from L2 in n over 2 dimensions or whatever dimension we have here into L1 in the big space. And when you look at this mapping, the distortion that we talked about, this parameter, is really the distortion of the metric. So if you take the natural L2 metric on your subspace, you take this map out and it gives you L1 metric. And if the subspace had distortion delta, that's how distances will be distorted by at most, by at least 1 and at most delta. That's what it really gives you. So why is it interesting? It's really interesting because, well, this is, first of all, it's a big, Banach space. People work on metric embeddings, and it's a huge field, and I'm not going there, which is, but it's really interesting. But even for this specific case, often you look for such embeddings between metric spaces because you have a problem to solve in one of them, but you have efficient methods in another. So if you have a mapping that doesn't distort distances by much, like, for example, approximate nearest neighbor search, but there are many others, then you can get an efficient algorithm. So this particular example, what is it? It's you get a set of points. Maybe you can pre-process them, and then you get another point, and you ask what is from my original set, which is the closest, or which is roughly the closest in L2, right? And you don't know how to solve it. It's a complicated problem, but it turns out that if you're using this embedding, you move it to a slightly higher dimensional space, but L1, and in L1 also this point moved, but it turns out that in L1, what the search will give you is very close to what you'll get. You can control the parameters. I'm not going into this. The solution in this space will give you back a solution at that space that will be of high quality. So this is the type of reason to do this kind of embeddings, just getting efficient algorithms. Yeah.
Again, if I'm not an algorithms person, so here there's just something that's like exponentially faster searching here.
It's not exponential. I don't think so. Yeah, this is much more efficient because approximate nearest neighbor in L1 is easier. What we know today is just faster than what's known in L2. So you just do this transformation, solve it here.
By more than a constant factor, because you're going
in time by more than a constant factor, but the approximation doesn't go up by more than a constant factor. The approximation is, I think, within a constant factor. Yeah. Okay, so that's one reason to do these embeddings between different metric spaces. Another reason is this wonderful compressed sensing. So for those of you who don't know, let me tell you what it is. A very simple, very natural problem. When in lots of measurements, in particular when you take pictures, in lots of signals, there's a huge sparsity, right? So when you take a picture of this room, there's a huge sparsity. Maybe it's not in the obvious basis, but there are obvious bland spaces and then unique features and so on. It can be compressed a lot. So it's sparse in some basis, and the basis for us will just assume it's a standard basis. So we have a vector u in n-dimensional space which is sparse. It has just s non-zeros, okay, s out of n. Think of s as small, relatively small. And you want to retrieve it from some linear measurements, maybe optical, maybe something else. CAT scan, I don't know. So what you get is not u, but actually a linear transformation a times u. So you get this z, and you want to know what u was, and you know it's sparse. Okay. The question is how few, how many equations, how many linear functions of u, and which linear functions of u should you take in order to recover u from z. So the problem you have to solve is basically this. You want to solve, u will be the x, which will minimize this quantity. So you want z minus a times x, so you want to shift it by ax in such a way that the result will have few non-zero coordinates, right? So that's a minimization in L0, in support size. And that's, unfortunately, NP complete, NP hard. So you can't really solve this. You can do something else which is feasible, which is, let's do the minimization in L1. Right? L1 minimization is just linear programming. That's efficient, so you can do it. So you get another vector, u star. The question is, what's the use of this? It turns out it's really wonderful. This observation is compressed sensing, right? This observation is compressed sensing. If your matrix represents a subspace of low distortion, then you'll get the same answer from both. So this is the work of Dono and Candace-Tao. If X is the kernel of this matrix A, then as long as S is not very, it's supposed to be sparse. So sparse means n over the distortion. If the distortion is constant, even linear size vectors, you can recover. The solution to this program and this program will be the same. Might as well do the efficient one. Okay? So the proof, I could give it to you. It's a couple of lines, but I won't now. Maybe you can ask me about it. But it's just the fact that in this subspace of in any subspace of low distortion, when you take a sparse vector and add to it a non-zero vector from the space, the L1 will go up. So the minimum for the L1 will be the sparse guy, the minimum in L0. And it's a very simple proof, just from the definition. Yeah.
So it's for every sparse vector or something?
Every sparse vector, exactly. So, every sparse vector, yes. Now, somehow in this application, the way I described it, U is the information. U is what you want. And X is sort of the noise that you want to get rid of, which you can get rid of in the case of a good distortion subspace. But actually, Candace and Tao also suggested that you can look at it the other way around, where X is the information and U is the noise. So think that you are trying to send some message over the reals. So you encode it by some linear error correcting code. So you're getting X is a member of a subspace. That's what at least a linear code is over finite fields. And then if somebody perturbs it in a few places, so by a sparse vector, and remember, the magnitude shouldn't matter. Just as long as it changes a few entries, even by huge amounts, you want to recover the original thing. It's basically the same problem. Because you recover U, you recover X. You recover X, you recover U. So that's, and they observed that if you do it, here just written what I said, that such a subspace can be a good code for every one of it, every such element of the subspace. If you perturb it by a sparse vector, using this same linear program, you can recover. You can get rid of the sparse vector and then.
Actually, what's U and what's X somehow?
Yeah, so U is a sparse vector.
Yeah.
And X is a member of the subspace. So in this coding theoretic framework, you have a subspace is a linear code. Here it's a code over the real, so you can encode real numbers by longer vectors of real numbers, a vector of reals by a longer vector of reals, such that if you add to it any sparse vector, that's the noise, right? A simple program, an efficient algorithm, will find this thing, will eliminate it, and will leave you with a code word.
I think in your notation, you probably are X, what you're calling X is Z minus AX. That's probably why.
Oh, that's like the.
Yes.
Oh, here. So I changed, I guess I changed notation.
Starting from the proof.
Yeah,
X
so,
changed.
yeah.
Yeah.
Okay, yeah. So, even, so that seems right. So, but stay with the high level with me. So we have a linear combination of an element from a low distortion subspace and a sparse vector, and we can recover both. We can separate the two using a linear program. That's the main observation here. And this is via a linear program, so that's great, and it's polynomial time. And now once you have a polynomial time, you start worrying about efficiency. Can we do better? And the good news is here again using expanders, and that relates to the previous thing, is that you can actually, if you pick your code appropriately, then you can get actually a recovery here, the separation of noise from data in near linear time, not just in polynomial time. So I want to show you how to do that. Everybody's okay, except the first row that I don't really care about. Okay, so expanders, just a quick slide. Sparse graphs which are highly connected. In fact, they are what you should think of as a random graph, in the sense that for every two subsets, the number of edges between them is what you would expect in a random graph with the same degree. So the n large number n of vertices, but the degree is maybe fixed, or anyway small, regular. And for us, actually, the property that will be relevant in such these graphs have many wonderful properties, many wonderful applications. For us, what's relevant is that edges are spread. They cannot concentrate on a few vertices. If you have some fraction of the edges, then roughly they'll touch roughly the same fraction of vertices. They cannot concentrate. That's what we'll use here. And the other important thing about these expander graphs is that we have efficient ways of generating them. Many, many different one, algebraic and combinatorial. We can build expander graphs, and we need to. So how are expander graphs going to help us construct our codes and actually help us construct the Euclidean sections I talked about with low randomness? I will not really explain it. Is that we are just going to imitate what was done with codes over finite fields. Just transition everything to the reals and everything will work. So what was that? I don't know if you know about this. So starting with the work of Gallagher at MIT in the 60s, his PhD thesis, he explained how to build linear codes from graphs. And I'll explain to you how to do it in the case of reals, but it's the same. I'll use what's called tunnel codes, a variant of what he did. So how does it look like? How do you take a graph, a sparse graph, and build a code? That's what you do. So in some sense, it's going from local to global. So we take our graph, a deregular expander graph, and assume we already have a good code. So we have a good code, but just for like a constant size code, a code on words of length d. Think of d as a constant for now. Okay? Suppose we have such a code, then we can build from it a code over, in n-dimensional space, and n can be whatever we want. So just that's the idea from this local to global. So we have a local code, and we are building a global code, which we'll call x. So it's a subspace. We are building a subspace. And the space we are embedding it in is a space of functions over all edges. Okay, so we'll just have vectors which are just labeling the edges with real numbers. So let's label the edges with real numbers here. And let me tell you when it is a code word. So when is it a code word? Well, we have codes of size d. So d is exactly the degree. So every vertex should look at the edges touching it and say whether it's a code word according to the local code. And if all of them, so here's our word, so function over the edges, and it's a code word if, this vertex look, A, D, E is in the local code, good. Every vertex is checking it. If all of them are code words, then the whole thing, this big word, is in our new code, the global codex. Okay? So that's a construction of a big subspace from a small subspace, according to an expander graph. Okay, so what's the property of this? Why are these codes good? They're good because of the following. So assume that, okay. It's good because if the local code was good, then the big code will have not only will have good distance, but will actually, so good distance means that you can perturb it by a sparse vector and still recover the information, but you can do it efficiently. And efficiently now is not no linear program, it's just standard belief propagation, which if you don't know what I mean, I'll just tell you. I don't know if you noticed that now I put arrows in the, so here is the original vector. Now somebody came and spoiled a small fraction of the edges. Just some of them are stars, some arbitrary values that are arrows, or just arbitrary values. And we want to recover them and recover the original data. So the way to do it is just, the belief propagation says the following, every vertex, look at the edges touching it, and if most of them are consistent with the local code, then fix the ones that don't look like in there. Put actually the unique code word that fits there. So just correct the wrong edges if they happen to be few next to you. Every vertex does the same. And it turns out that in logarithmic number of iterations, you'll eliminate all the errors. And the main reason, or the only reason for this, is what we said before. Edges are spread across vertices. So if you have some fraction of edges, and it's not too large, right? We have a sparse vector making the error, so there are not too many errors, which means that on most vertices, there are not too many local errors. So most vertices will correct correctly. Some vertices may correct incorrectly, but overall, you'll be making progress, and in log n rounds, you'll finish. That's the reason these codes work both over the finite fields and over the reals.
Was Gallagher already using expanders?
So he was using random graphs. There were no expanders in the 60s, so he was using random graphs. It's the same story with von Neumann and fault tolerance for circuits. He was using random graphs, and then people used expanders. That's the end of the second story. Just perfect, an hour. So we can stop, or there's, I think, 15 minutes of some more fun, but I think that Madhu will, you decided?
What, we should go on?
Go on, yeah. So this is a person to blame. So I'll let people who really, I'm sure that people didn't plan on my slowness here. Okay, so.
I'll tell you later.
Okay, good.
No, Madhu
You don't
warned
want to
us.
share what?
Madhu warned people that you like to talk.
I don't know if the warning was, did you give them the complete warning or like how much I like to talk? Okay, so the last one is, I made sure that it will be short. Okay, so I want to tell you about different work, different kind of problems. And these are really the most basic problems in geometry. They are about incidences of points and lines. And actually, there's a whole thing that I'm not, because I confine myself to the real geometry, to Euclidean geometry, I'm not telling you about beautiful, beautiful results that have to do with point line incidences over finite fields, over prime fields, and their applications to very beautiful stuff in theoretical computer science, extractors, and so on. But let me tell you about this Euclidean geometric result. And here's a start. I want to define special lines. Okay, so you have a configuration. You have some points and some lines in space. Okay, and what's a special line? Well, a boring line is a line that passes through exactly two of these points, this typical line. But some lines are special in that they go through 3 points. That's like a coincidence. That's something that's special. So I call them special lines. Okay, so this is a special line. This is not a special line. Okay? Okay, good. So suppose you have endpoints in space, and now you look at all lines through them. Okay, just pass all lines that go through at least two of them. Yeah, so I said here this, it's called the Sylvester-Gallai Theorem, what I'm going to tell you, but actually, it shouldn't be called that because Sylvester is one of the people who conjectured it, and Gallai is one of the people who proved it. What should be actually called is a Sylvester-Erdős conjecture. There was independent conjectures, and these are two people who independently solved them. But at least one relation is clear. Erdős conjectured it to Gallai, and Gallai solved it for Erdős. So, anyway, what's this beautiful theorem? It's really, really simple and neat, and actually it's a nice challenge to prove. I can show it to you later if you want, or if you want to think about it. It says the following. Suppose that all lines are special. Okay, every line is special. Every line through 2 points passes through a third. Whatever you try, that happens. Okay? What kind of configuration can it be? Anybody has an example of a situation where this will happen? Yeah, very good. So definitely, if all of them are on a line, this will happen. Any other example? Good, because there is no. That's the only way this can happen. So this is the theorem. This theorem is, as I said, is beautiful, and as many such beautiful results, is not satisfactory because life is not perfect. And in lots of situations, the information we have is not about everything, but about almost everything. And in fact, the last 10 years have seen so many of these examples in analysis, in geometry, in PCPs, and various encoding results, beautiful results, where you take some theorem like that, and what you really need is an approximate version of it, in the sense that if the assumption is almost satisfied, is it true that the conclusion is almost satisfied? Okay, and I'm not going to detail on this, but you have enough people in this, here at home, at Microsoft, who can tell you much more. But I'm going to talk about just this particular case. Okay, so here's an approximate assumption. What's the approximate assumption? Most lines are special, or more specifically, suppose that for every point P, a constant fraction of the points is on special lines through P. Okay? Suppose that that's what you know. Is it true that you can conclude that they are all on a line? No. Very good. There are many counterexamples, in fact, I mean. So that you cannot conclude this. I mean, for example, take the grid. I mean, the grid, take any point, all the constant fraction of points around it will, you pass, there will be, you'll find a third point, right? If you're just close. That's one way. Another way, maybe that's the way thing you thought about. If you take 10 lines arbitrarily in space, and you put n over 10 points on them, that will also be satisfied. So if you would just have many special lines, that there are many things. But you notice that this is in 2 dimensions, this is in 20 dimensions. Maybe we can conclude that the only situation where this can arise is that all these points, even though initially they can be in arbitrarily high dimension, maybe they are restricted. And you can conclude this. So this will never happen in more than 1,000 dimensions. That's the result. So more specifically, let me tell you the general result. So you can always conclude that they'll be limited to a low-dimensional space. Here's a theorem that's joint work with Barak, Dvir, and Yehudayev. So this approximate version of the Sylvester-Gallai Theorem says that if to every point P, at least delta n of the points are on special lines through P, then the whole configuration must be confined to a low-dimensional space, which is a constant depending on delta, 1 over delta squared. So that's the approximate version. We don't know if it's tight. 1 over delta is certainly a lower bound, and we are somewhere between 1 over delta and 1 over delta squared. And I'll tell you something about this theorem. But I want to say that this type of technique that we are using leads to approximate versions to other interesting results in combinatorial geometry. By the way, this is false over finite fields. So it should be noted. The real or large enough fields are very different than small fields. This cannot be done over, it's false over finite fields. And actually, that was part of our motivation. And this result has an interpretation for error-correctable codes, which I will not state here. But I want to say that the same type of techniques give approximate versions to other famous results in combinatorial geometry. The Motzkin-Rabin theorem, it's similar to Sylvester-Gallai, but the points are colored. And Kelly's theorem, which is a higher... and Kelly's theorem, which is not about lines, but k-dimensional sets, so just higher dimensional versions, and so on. So you get appropriate generalizations of these to the approximate setting.
Sorry, what do you mean by dimension here? So the points are in
So
higher dimension?
They're all, the all points are in a lower dimensional space. So you just what it means. So it's just a span. The affine span is of dimension 1 over delta squared.
But so affine subspace of that.
Okay, but you begin with the points on the plane.
Yeah, endpoints are in end. No, I didn't begin with them on the plane. It's just that the screen is plane.
No, I get that. So,
you start with endpoints anywhere in n-dimensional space.
Yeah, okay, I get it in a way, but so can you prove it if the points are just in 2 dimensions?
But if they are in 2 dimensions, then they are in 2 dimensions, so there's nothing to prove. You want to say that no matter how anybody arranged them so that there are many special lines, they couldn't have arranged it in intrinsically high dimension. Okay?
I think the question is, if they are already in the plane, maybe there's a stronger structure you can do.
Maybe, yeah, absolutely. There may be a strong, and there are that's right, and it's an interesting, right, because you can ask for more, are there few, in this case, are there few lines?
Right.
Yeah, we don't know.
What if it's not for every point, that you can just take those out?
So it turns out it's not obvious, but there are several other theorems there, and one of them says that just if there are many special lines, like constant fraction of the lines are special, but not through every point. So just an average case version, if you will. If a constant fraction of the lines are special, then a constant fraction of the points are in low-dimensional space.
In some sense, the grid example shows that, I don't know if that's Emmanuel's question, but somehow the grid example shows that you can't expect the conclusion to be a union of a finite number of lines.
Yeah, that's absolutely true. That's
Sorry?
so it's back to not to your remark, but to Emmanuel's remark. If they are already in the plane, the grid example shows that you cannot say that they are on a constant number of lines because.
No, but a grid is kind of a very nicely structured.
Yeah, exactly. No, that's right. Yeah, absolutely. So if they were generally in the plane, there will have to be a grid. Maybe, I don't know. That's a good question. Okay, so let me just tell you one slide about the proof, which is really our initial motivation. It's the kind of thing we were trying to understand, and that we arrived. We couldn't understand what we wanted to understand, but what we understood is its geometric consequences. So that's what we wrote up. So what we are really trying to understand is what structure of the zero non-zero pattern of entries of a matrix can tell us about the rank. In which cases does it force high rank? We know if you take a matrix and all the off-diagonal entries are 0 and all the on-diagonal entries are non-zero, then it's full rank. Doesn't matter what the values are. So, let's generalize this. And it turns out the questions of this type come up a lot. And in some sense, they are really crucial, let's say, for proving lower bounds. They come up a lot, but people study them in graph theory, in game theory, and they're really, of course, varieties of them are really interesting. So here's what we were looking at. So let me tell you it from the point of view of the proof of the theorem, but actually I'll get to the structure immediately. So this is the theorem stated. Here's the collection of points, maybe in high dimension. So just write, each point is a vector, maybe n-dimensional vector. We want to prove that they are all in low dimension. How can you prove that? One way to prove it, maybe very indirect, in some sense counterintuitive, is to find a matrix that kills them all. Okay, find a matrix that kills them all. So this matrix product is a zero matrix. Okay, you want to prove that this is in low dimension. One way you can prove is that this is in high dimension. Right? So we had n points, so there are n guys here and n columns here. If you can prove that this is in very high dimension, this has to be in low dimension because the product is 0. So it's sufficient to prove that the rank of this matrix is very, very close to the maximum, to n. Okay? Okay, so do we know that we have such a matrix? Of course we know. We have many special lines. Special lines are relations, linear relations between the points. Right? If you have 3 points on a line, you have a linear equation. Okay, good. So we have these linear equations. In fact, linear equations with 3 ones per row. So that's one already condition. They are sparse equations. In fact, we get more. We get what we, you need to prove that you can get more, that you can get you take an appropriate subset of these relations of special lines, and then you get a matrix. The matrix here will have the following structure, what we call a KQT design. Basically, that there'll be a few non-zeros in every row. There'll be many non-zeros in every column, but every pair of columns will have a small intersection. That's a design. And what we prove is that such matrices have high rank, indeed. So what we prove is that the rank of any such matrix is n, the maximum, minus something that depends on these parameters, but when these parameters are what we get, this is a constant. Okay? So that's how we prove it. I will not show you the proof. It's not that difficult, but there are several things. Well, you need to generate the structure from the conditions here, which is one part of the complication. But even after you have this design, there is one part of the proof which is sort of standard spectral argument, but that you can do normally in all the applications I know when all the entries, the non-zero entries, are bounded in magnitude. They are, at most 1 in absolute value or 10 in absolute value. You cannot apply spectral techniques, L2 norms, and so on if entries can be unbounded. And the second part of the proof is using, the first part of the proof is to use what's called matrix scaling, which is a way to change the entries of a matrix basically by multiplying the rows by a constant and by constants and the columns by constant. And you have to see that you can do it, and you have to see that if you do it appropriately, nothing that you care about changes. Of course, such linear relationships will remain true. Of course, the rank is not going to change by such multiplications. And anyway, you check what you need to do. And it's a really fantastic technique to understand in some situations where you have arbitrary matrices with arbitrary values, and you want to control them, you can do it under some conditions which happen to be satisfied here using matrix scaling. Okay, so that's it. And here is the open question which we set out to prove, and many people set out to prove since Valiant wrote this beautiful paper in the late 70s. Find what we really want is matrices which are rigid. Rigid matrices are just matrices which not only have high rank, let's say linear rank, but they have high rank even if you perturb little o one of the entries. A random matrix is like that over any field, but we don't know how to, find explicit ones. So summarizing, TCS goes hand by hand with geometry, with analysis, with all. So I could have given, I'm sure, probably an hour on maybe 6 of these 8. But maybe not on all of them. So basically the message is that algorithmic and computational issues, of course they need mathematical tools. That's so the obvious direction, but they also bring new mathematical problems and also new techniques to solve mathematical problems, and you saw in these examples. And the questions, I remind you, the 3 open questions I asked, I'll be happy to hear of solutions. Thank you. Questions?
Do you have a sense of what should be an explicit spherical cube? I mean, what would a description possibly look like?
It's really, the guy can try to help. I really have no sense of what it should look like. Because let me show you the construction.
This is the what?
The spherical cube.
It's like 2-dimension? What is it?
If you asked a different question, it would be a different slide, but yeah. How it should look like, in what. So what we are constructing is not really the bubble itself, but we are constructing its spine. Its spine. So let me define it. It's just 2 slides. A spine is a surface that blocks all the cycles which wrap around. So in this periodic thing, you have like in the torus things that wrap around. So in the square, any such surface, so in this case it's just a line, blocks all circles from here to here, right? Because you have to cut this spine, and similarly, it cuts this. So the claim is that any spine gives you a bubble, gives you a periodic unit volume structure. Why? Because you just draw it, You just draw it, and you see that because it blocks everything, it will be enclosed. There will be no escape, right? So it's any spine gives. So what we are constructing is actually a spine. Now, how do we construct this spine? Yeah. So it's in high dimensions. The way you construct this spine is you start from something that looks like what you want. It's just like something with low volume, which fits inside a unit cube. Okay, it will actually the largest thing that that's the isoperimetric problem that's well known and well understood, and that's the thing you start from. And it's actually of exponentially small size, this guy. But anyway, you start, and it turns, so it's an exponentially small size, but it has the best, what you are looking for is the best. This isoperimetric problem you want to solve is that the surface area of this bubble, or what we call a pre-bubble, to its volume is square root of d. So you can achieve it. Inside the unit cube, you can put a...
Yeah, I just wanted
This ratio is what you get for the unit
Ball.
unit
Yeah.
volume ball.
Yeah.
But if you make the ball smaller,
But the unit
No, it's not a ball. So,
but the ball, if a unit volume ball is not contained in the cube, and if you just make it smaller so that it becomes contained, then the ratio becomes d, not square root d.
Yeah.
Okay. All right. Thanks.
That's really, yeah. So it's not the solution to this problem, even though without this containment restriction, it's a ball. Inside the unit cube, it's not the ball. The ball is not the best. It's far from the best. Right. It's a product of sine squares. I mean, what do you expect? It's.
You have some picture of it in 3D or something.
Yeah. Actually, so I mean, in the square, it would look like something that looks like almost. It will look like a shape like this. It's a continuous curve that just slides around the edges. Okay. Excuse me? You know B. B is B is well known. It's an eigen. What?
Even B, we kind of know it. It's some level set of a specific function, but even we don't know which level we.
You know it, but it's not like you say, it's not that explicit. Yeah, but anyway, this is not the non-understood part. I mean, it's just the beginning. So you take such an object, and what you do to generate the spine is you throw it in randomly. Now, really randomly. Think of this as a torus. Throw it randomly in this torus, random shift of it, and take the surface area as part of your spine. Take another random shift, and take whatever is not covered yet to be in your spine. And throw another one. It's a torus. Take the surface area. Throw another one, and just keep throwing them. Until you fill it up. Because it's it has some positive volume, exponentially small in d, but positive after this process will end. What you'll get when you get when it ends, it's a spine, and this is a spine that defines the bubble. Terrible. And let me just say, because of this property, what you need to show is that this property is maintained. Right, so this ratio of volume to surface area remains. You don't.
Because it covers the entire.
Because it covers the entire space. Yes, you'll cover the entire space.
So is there any relationship between solutions for different values of
D? No, not as far as I know.
they're completely
No, I mean what you start from. The solution to B, the solution to this body. I mean, it's sort of uniform indeed. Just it's a product. It's whatever describes D is very simple to describe in a way that's uniform in D. Okay, but then you start throwing them around, and there is no solution. Anyway, it's a probabilistic argument. Yeah, it's an existent proof. Right. As you saw, I don't have any more slides, so whatever questions you ask, there'll be enough slides coming with it.
You promised that you have a 3D picture, right?
No, I didn't say that I have a 3D. I said that we have in the paper we have 3D pictures, okay. Even in color.
All right. No further questions. Let's thank Avi.